Hi everyone, we're going to start part one of alkynes now. And let's start with a review of alkanes, alkenes, and alkynes. So first let's draw out the Lewis structure for ethane, and ethine, two carbon hydrocarbons. So there's different ways of doing this. I'm just drawing sort of, just a random Lewis structure like that. If you want to do the dashes and wedges, that's totally fine. Or you could just draw them out, with all the H's just sticking out into a cross, even though it's tetrahedral. But in any case, you should have two carbons connected to each other, 6 hydrogens. Go ahead and do ethene and ethine as well. Okay, so in this first part, pretty straightforward, but just a reminder that we've got carbon, it's the tetrahedral, trigonal planar, and linear. We've got the octet rule in all of these cases, and you've got different degrees of unsaturation, so no degrees of unsaturation, 1 degree, and 2 degrees because of the pi bonds. So let's label the sigma and pi bonds on each of these. All right, here we go, all sigma bonds. Those are head-to-head overlapping orbitals, usually s orbitals for hydrogen, and sp3 or sp2 or sp hybrid orbitals for carbon. So here it's sp3 hybridized carbon, sp2, and sp. Okay, so let's label those as well. And remember, the second bond of the double bond is a pi bond. The second and third bonds are pi bonds for triple bonds. And their pi bonds are generally weaker than sigma bonds. So let's remember for carbon, that's tetrahedral, it's sp3. So that's going to have a bond angle of 109.5 approximately. This one's going to be sp2, meaning it's trigonal planar. It's got that unhybridized p orbital that's overlapping to make the pi bond. So this is 120 degrees approximately. And here we have an sp, which means it's about 180. So 2 pairs of unhybridized p orbitals that overlap to make the 2 pi bonds. Now the shortest carbon-carbon bond is going to be the one where the electrons in the bond are held closer to the nuclei of the atoms they belong to. So for example, when we talk about %s character, that's referring to hybridization. So let's think about the type of hybrid orbitals. sp3 has 1 s orbital and 3 p orbitals for a total of 4 orbitals that got mixed together to make an sp3 orbital. So if you think about how much of this sp3 orbital, and just to remind you, we've got sp3, 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 and sp3. This carbon has 4 sp3 orbitals. That's why it's tetrahedral. So each of these orbitals, okay, is an sp3, which means that it's 1 out of 4 orbitals is s and 3 out of 4 orbitals is p. So %s character for sp3 is going to be 25%, 1 out of 4 orbitals. For sp2, it's going to be 1 out of 3, so 33% s character. And for sp, it's 1 out of 2, so 50% s character. That's telling us the greater s character there is, think of more contribution from an s orbital, which is closer to the nucleus. Remember how electron configurations go? 1s2, 2s2, 2p6. I can't even remember right now. It always starts with the s orbitals, and the 1s being the closest, 2s being closest. So for carbon, its valence electrons are in 2s. It's going to be closer to the nucleus than if it were in a 2p orbital. So that 50% s character is bringing those valence electrons inward. You have a higher effective nuclear charge, and that those electrons are going to be more stable. And so when the electrons are brought in closer, that makes these bonds shorter and stronger. So I put greater s character. You're going to have electrons held closer to the nucleus, valence electrons, and you're going to have stronger and shorter bond as a result of that. So let's see how that affects acidity for these hydrogens. How likely are these hydrogens to come off? Now first, you probably know none of these are really good acids. They're all very weak or very poor acids indeed. But it's possible you could pull off hydrogens if you had a strong enough base. So what would be the conjugate base if we removed one of these hydrogens? What would that look like? So I removed a hydrogen and I got CH2 instead of CH3 and a lone pair. So basically I'm thinking of this electron pushing mechanism. Base comes in, grabs an H, and then deposits the electrons from this bond onto the C, and the base grabbed the hydrogen H+. Okay, so then you end up with this lone pair here and a negative charge as a result. So same thing here, pull this off with the base, you drop the electrons onto this carbon, you get a negative charge, and same thing here, one of these hydrogens. Doesn't matter which hydrogen you pulled off, just take, because they're all equivalent in these molecules. These 6 are equivalent, these 4 are equivalent, these 2 are equivalent. So it doesn't matter whether you pulled it off here or here, by the way. Now thinking about S character, that sort of tells me how close or how far the electrons are held in this atom. So for example, if I have sp3, and I know that's sort of a big orbital because it's mostly p character, it's going to be farther from the nucleus. And then this is going to be a little bit closer than that because of a greater S character. And then this is going to be even closer than that because it's even greater S character. So you have a sense of which of these lone pairs is more out there and available for bonding. It's this one. So this is our strongest base because the electrons are out there. They're more reactive. They're more able to bond with things. Here these electrons are held closer in, greater effective nuclear charge. So the nucleus is positive. So those electrons feel more of a pull inward rather than being accessible for a reaction. So that means that these are more available for bonding. That makes them a stronger base, more reactive. These are held closer in. That makes them not as reactive. That means it's going to be the weakest base of this series. And that's because of a greater S character. So I put that this one is less reactive and held closer to the nucleus because of greater S character. So that means that if this is my weakest base of the series, then it has the strongest conjugate acid. Because remember, reactions go a certain way. So if reactions like to go this way, then they're not so good at going that way. Okay, so let's say that I have this alkynyl ion that we had before. And I'm saying this is a weak base because these electrons here are held closer to the nucleus. So if that's true, then this does not really like to go backwards very much. This is not effective, so it doesn't go backwards, but rather this loves to become this because this is more stable. So weaker base is definitely more stable. Well, more stable than what? More stable than this guy. So this guy wants to go this way to become this. So that means this base will come by, grab this H, deposit the electrons there, and that will happen more than this grabbing this H and going backwards. So the equilibrium favors the products. So that means this is going to be pretty good acid compared to the acid of this or the acid of this. So that means it should have the lowest pKa of the series. If this is the weakest base, this is the stronger of the conjugate acids. So the stronger the acid, the lower the pKa. So do we see that? Alkanes, generally, you should just memorize this, by the way. Alkanes have a pKa. These hydrogens tend to be about 50 pKa units. This tends to be about 45, and let me label this pKa. This tends to be about 25. It depends on other structural features as well, but generally speaking. Okay, so you could see every pKa unit, by the way, is a power of 10. So this is not 20 times different, it's 10 to the 20 times different. Okay, so that's a lot. Now it's probably a good time for you to sort of start getting a better grasp of this. I know in the past I let students use this chart in Chem 261, but it's time that you start taking off those training wheels. So let's just start with alkanes, our pKa of 50 in general, assuming no other functional group. Okay, 45 for alkenes. You notice benzene is also like an alkene, but it's actually resonance stabilized. It's a little different. But these are still, not very good acids. If you can, we'll learn about amines more in Chem 263, but they are pretty high pKa also, meaning not very strong acids. So this is the weakest acid up here, has the highest pKa. And the strongest acid, by the way, here's the alkyne. Okay, so generally, why don't you just start by learning these? Okay, so it makes it a little bit more manageable when you just learn a few. And then you should already know your strong acids just from Gen Chem 3. Strong acids have a very low pKa. So strongest acids, in fact, they're just called strong acids. Even though it's a continuum, there is no strong versus weak. It's just There's strong, and then there's less strong and less strong and less strong. So strong acids, whenever you see the term strong acid, they mean these specific ones usually. And then everything else is considered weak, even though there's different levels of that weakness.